Welcome back to Meaning from Data, Statistics Made Clear. In this lecture, we're going to talk about the bell curve. Recall that when we know all the data in a population, what we're trying to understand about the distribution is its shape, its center, and its spread. And an effective way of understanding a set of data is to compare the data to some model shape. And one of the principal methods for describing distributions of real data is to describe some known idealized distribution. For example, in the last lecture, we introduced a couple of such families of shapes of distributions, the Poisson distributions and the binomial distributions, as well as the uniform distributions. So our strategy then is to use these ideal distributions and use them as models and then compare the real data set with one of these as the paradigmatic model of what we're after. Well, the most famous shape of distributions ever is the bell-shaped curve, which is called the Gaussian or the normal distribution. And so the family of curves that is the normal curves or the Gaussian curves is the topic of this lecture. I think the best introduction to the normal curve is just to look at a bunch of examples from all sorts of sources to see how common this shape arises in the world of how commonly it arises, I guess. How common it is or how commonly it arises. So later in the lecture, we'll talk about why it's so common. But for now, let's just look at a bunch of examples. So here is the first example, is the histogram of the heights of male adult American males. Here's the next example, the heights of American females. The next example is the histogram of the year 1920 Major League batting averages. Here's another example, histogram of the year 2000 batting averages. Here's an example. This will take a little bit of explanation. This is an example of the following. Suppose that you have a deck of cards and you take up 5 cards from this deck. So it's like a poker hand, except I'm not going to be talking about the way poker hands are evaluated. Instead, let's just evaluate the cards 1, 2, 3, 4, 5, 6, up to 13, where that is the jack is 11 and the queen is 12 and the king is 13. And then you take 5 cards, you're dealt 5 cards, and just take the average value from those 5 cards. So that's the average, that is the average of those numbers, is called the average value of those cards. And if we looked at all possible 5-card hands of that sort and looked at their average value, we would get a histogram that looks like this. Notice again that all of these examples have this characteristic bell shape to them. From the last lecture, we saw an example of that the binomial distributions had this bell-shaped character to them. The binomial distributions, you may recall that we talked about taking all samples of size 50 of, say, 20-year-olds and seeing what fraction of these different samples had 1 graduate, 2 graduates, 3 graduates, and so on. And drawing a histogram of that gave us once again this bell-shaped curve. So in this lecture, what we're going to try to understand is what the normal distributions are. We'll describe a mathematical description of them, give a specific mathematical equation that gives this bell-shaped curve as its graph, and then we'll see why it is that these kinds of things arise. We'll also give a method for creating distributions automatically from any starting distribution, doing a process that gives a bunch of bell-shaped normal distributions that arise from it. But we'll begin our introduction to this normal or Gaussian curve by looking at a little bit of history. The term Gaussian celebrates the famous German mathematician Carl Friedrich Gauss, who lived from 1777 until 1855. In 1801, he was a young man, and there was an observations were taken of the first asteroid ever observed, the asteroid Ceres. After a few observations, the Ceres passed behind the sun. And the question was how to find it after it emerged. Well, Gauss was able to predict the future position, where to look for it after it passed the sun, by looking at the past measurements and these past observations, and realizing that observations, like all measurements, include errors. They're always off. All measurements are off. And what Gauss was able to do was to fit a curve into the observed data that would minimize the error between the curve and the known observations. And in doing this process, it involved this kind of distribution of errors. So in fact, this distribution of errors had this bell-shaped curve to it, and it was so commonly associated with errors, such as in measurements, that an old name for the Gaussian or normal distribution was the error distribution. And that's just because measurement errors are so common, and they always produce a normal distribution about some center value, so to speak, the real value. So the error curve suggests one of the reasons that this symmetric value arises, that it's somehow an error on one or the other side of some correct value, but you can't quite get it right. So it turned out that although Gaussian distributions were associated with errors, later they became associated with the distribution of other kinds of things in nature. And the first person to apply the Gaussian or normal distribution to other kinds of arenas was a gentleman by the name of Lambert Adolphe Jacques Quetelet, who lived from 1796 to 1874. And he was the first to apply this normal distribution to settings other than errors. In his book, Sur l'homme et le développement de ses facultés, essai d'une physique sociale, in 1835, Quetelet introduced the concept of the average man, l'homme moyen. Well, the concept imagines that you have an average person around which all the people in the distribution are distributed according to a normal distribution. And for many characteristics of people, such as height, chest size, if you draw a histogram of the data about all people in a population, sure enough, you get a bell-shaped kind of a curve. Incidentally, Quetelet introduced the body mass index, which is still used today to define obesity. Well, but the normal distribution of these measured characteristics was in the 19th century was taken almost as a law of nature. So people who had extreme values, such as, say, being very tall, began to be thought of as being abnormal. They deviated from the normal. So, in fact, maybe this is one reason that some people don't like the normal curve, because in a way it defined abnormal. Before that, I don't know what the psychology was, but maybe there is some substance to that history. Well, let's talk for a minute about why the Gaussian distribution will arise so frequently. One reason is that many times that if we're taking some value, and that's what we're measuring, and that value is actually the result of a lot of little influences that are randomly increasing the value or decreasing the final value, then that's likely to give a distribution that has a center value and then some pushing some values to the left and some to the right. Now, let's take an example. The heights of men. Well, if you think about what it is that causes us to be a certain height, in a way, presumably, the reason has to do with a lot of small genetic and environmental influences that sort of independently push us either a little taller or a little shorter. So they give pluses and minuses to our height that tend to sort of average out to the average. And so if you have a large population, we'd expect that most people would have the influences sort of balancing out and sort of canceling to give it sort of an average height, whereas a few people would sort of randomly have a preponderance of these influences that would lead them to, say, be extremely tall. So this is a way of understanding in general why we would expect this sort of bell-shaped curve for large populations and measurements such as height. If we take errors in measurement or random noise that often occurs, well, what's happening in random noise or measurement errors? Well, it's a combining of errors that sometimes give things to the plus side of the error and sometimes to the minus side, and that tends to accumulate into this kind of normal distribution. Another example, when lots of people take tests, you expect some to be above average and some below average. Now, of course, they're probably not always just guessing their answers to these multiple choice tests, but maybe that's a good approximation to some of them. Well, in any case, all of these examples lead us to expect Gaussian distributions in many cases. And in the same way that there were physical characteristics that led us to expect a Poisson distribution in certain settings because of having, in the case of Poisson, things like the random arrival of cars at a toll booth, we expected it to generate a distribution of a certain shape. Well, we can now say that the Gaussian distribution will arise when we're in a setting in which there are influences that are equally likely to give more on the plus side and the minus side. Okay, but now let's take the step of trying to describe this normal or Gaussian distribution with some more precision. And so we'll begin by just making the simple observation that the normal distribution is bell-shaped. Let's, in order to describe the family of distributions, once again, this is a whole family of bell-shaped curves, let's just notice some things about how these distributions can be related to each other. For example, here are the heights of American males, and here are the heights of American females. And you can see that the difference in these two graphs, I'm sort of flipping back and forth between them, the difference is they're basically the same shape. The difference is just where they're centered. One's centered at about 68 inches, the males, and the females are centered at about 64 inches. So one of the ways in which two Gaussian distributions can differ is simply where they're centered. This is a smooth Gaussian distribution. We'll talk about the actual formula that gives this distribution, but we'll just use it to see that you can shift it over, and it is actually an exact match shifting over, and that gives an example of how the centers can be altered. Now let's look at another pair of graphs that will illustrate one other characteristic in which bell-shaped curves can differ. If we look at the batting averages for batters in the year 2000, we have this characteristic bell shape, and if we compare it to the batting averages of the year 1920, we have a similar bell shape, but it's more spread out. And in fact, we talked about this before, that in this case, it's the standard deviation of that differs. The standard deviation from the 1920 batting averages is bigger than the standard deviation of the batting averages from the year 2000. The batting averages in the year 2000 are more clustered together. And so these are two characteristics of normal distributions. Their center and their spread can differ. Well, that's all that can differ. The normal distribution is completely determined, in fact, by where it's centered and what its standard deviation is, how spread out it is. That determines an exact formula for a bell-shaped curve. So let's now turn to actually looking at the formula for the bell-shaped curve. This is a very formidable looking formula. And I put up these formulas not for the purpose of understanding every detail of the formulas, but just to realize that these formulas actually exist, and you could plug them into your calculator and actually get an answer or have it draw a graph for you. But let me just mention something about this formula here, that it involves several things. One sort of interesting feature is that it has two constants in it, namely E and the pi, the famous ratio between the diameter and the circumference of the circle, pi. And E and pi are the two most famous constants in mathematics. So it's interesting that the normal curve contains both of these very famous constants. But in this hard-looking description of the normal curve, there are two other letters. There's a mu and a sigma. Mu is the mean. That is to say, the center point for the bell curve. And sigma is the standard deviation. So it's a measure of how spread out the curve is. So that means that we can choose any specific values for mu and for sigma, well, as long as the sigma is a positive number. You can choose any positive standard deviation and any value at all for the center, for mu, and you will get a bell-shaped curve. If you plug it into your calculator, you will get a specific distribution, a specific graph. So when you do type that formula in, you get these graphs, some of which you've seen before. But there is a feature of all the graphs that make the normal distribution useful for analyzing data. For example, if we look at this normal distribution, so here we've plugged into our calculator that the normal has mean 0, it's a normal distribution with mean 0 and standard deviation 1, that we get this nice curve here. Now there's a particular point right here that I want you to focus on. Notice something that happens to this curve. It curves up like this, and then it's peaked, and then it comes back down. It's all symmetrical, in this case around 0. And let me ask you to look at this, at the way the shape of the curve changes. If you start out, the curve goes like this, and see my hand, it's tapering up, and then it gets steep up. Do you see how my hand is showing concave up? It goes concave up, and then at the peak, it goes concave down. And then it goes down and concave up again on the other side. Well, at some point it changes from being concave up to concave down. That exact place where it changes is the value that is precisely 1 standard deviation from the mean. So in the curve where we have standard deviation 1, you can see that the place right here that is marked is the place where the concavity is changing from concave up to concave down. Any normal distribution will have the property that a certain fraction of the area under the curve lies within 1 standard deviation away from the mean. In other words, there are always, no matter what normal curve that you have, the amount of material between 1 standard deviation on the plus side of the mean and 1 standard deviation on the negative side of the mean is equal to 68% of the area under the curve. So what the effect of that is that it allows us to make some to get some understanding about, for example, what fraction of the population is likely to have certain heights if we're looking at a population that's described by a normal distribution. Likewise, in a normal curve, you always are going to have 95% of the material that lie within 2 standard deviations of the mean. And you'll have 99.7% of the material that lies within 3 standard deviations of the mean. So the effect of that is that you can predict how much material is, for example, further away than 2 standard deviations from the mean. So let's look, for example, at the case of heights of men. Well, since we know something about the heights of men, that they are well approximated by a normal curve, when we compute their center and we compute their standard deviation, we can estimate what fraction of men are going to be between 5 feet 9 and 6 feet tall, for example. So if the 5 feet 9 is the mean height of adult men, and the standard deviation is 3 inches, those are approximately correct, then we would expect that 68% of men have heights that are within 1 standard deviation of the mean. Well, 1 standard deviation is 3 inches. That means that we would expect between 5 feet 6 inches and 6 feet tall, that's 3 inches less and greater than the mean, we would expect that 68% of men are in that height range. And within 2 standard deviations, so we go 3 inches lower yet, so from 5 foot 3 inches tall to 6 feet 3 inches tall, we would expect about 95% of men to have heights that fall in that range, because those heights are the ones that are within 2 standard deviations of the mean. And if you have different values of sigma and mu, then you will, those different values approximate the different data sets. In other words, for heights, the mu was 5 feet 9 inches, and the standard deviation was 3 inches. But we saw that you can have a Gaussian bell-shaped curve that has any center and any standard deviation. One excellent use for the normal curve is that it allows us to compare items that come from 2 different normally distributed collections. And we can make the comparison in a meaningful way. And the meaningful way is to measure how many standard deviations an element is above the mean or below the mean in one group compared to the other. And let me pin it down a little bit. In lecture 16, which is about sports, what we're going to do is try to compare baseball players from different eras. In 1920, we saw a graph before, in 1920, the mean was 265. That was the mean batting average. And the standard deviation was 0.05. So 50, in the way that you usually think of batting averages, was the standard deviation. In the year 2000, the mean was very close to the same thing. It was 266, but the standard deviation was smaller. It was 38, 0.038. So if we want to compare the performance of a batter from 1920 to a batter from the year 2000, we can compare these two by looking at the histograms of the 1920 batting averages and the histogram of the year 2000 batting averages and putting them next to each other in this way, and look at these 2 players. Joe Jackson from the year 1920 had a batting average of 382. Moises Alou had a batting average of 355 in the year 2000. But remember, the standard deviations in the year 1920 was 50, whereas the standard deviation in the year 2000 was only 38. So both of these values represent a player who was 2.3 standard deviations above the mean. So you see what I mean? That by looking at this distribution as a normal distribution, we can say how far above the mean the performance was of these 2 players. So in a way, the Joe Jackson's performance relative to his compatriots in 1920 is comparable to Moises Alou's performance of 355 in the year 2000, even though the batting average here was only 355 and the batting average was higher, 382. Both of them are 2.3 standard deviations above the mean. So in a way, that's a way to compare the data from different normal distributions. And such a measure that is measuring a value of a datum by how many standard deviations it is from the mean is called its z-score. So it's a way of normalizing and comparing where particular individual is within the distribution of values. And let me point out here, just with some pictures, that this concept of how much of the material under a normal distribution lies between a certain one standard deviation below the mean and one standard deviation above the mean. It doesn't matter what the shape of the normal distribution is. It doesn't matter if it is a squat distribution that has standard deviation 2. So this is one standard deviation above from the mean, and consequently this is 68% of the material under the curve, because it's one standard deviation away from the mean. Here's a standard deviation of 1.75, and so if we take the material that just is one standard deviation below and above, it's still 68%. So the point is that if you look at standard deviation of 0.75, that's a more peaked curve, still the material that's within one standard deviation of the mean is going to contain 68% of the material. And if it's very, very thin like this, standard deviation of 0.5, then still the material that's one standard deviation from the mean, 68%. So that's why the comparisons you see from things with different normal distributions and different spreads, we can get a sense of how much material is close is a certain distance from the mean. Let's look at the binomial distribution we saw in the last lecture had this bell-shaped curve to it. But let's go on to the average value of cards. Remember that if you have a collection of cards and you just take one card from the deck, the value of each one is it's going to have a uniform distribution. If you take two cards and take their average, then among all the collections of two cards that you take, you will see that the distribution of average values has this kind of a shape to it. And when we put more cards in, for example, 3-card hands, you take all possible ways of taking 3 cards from a deck, and then you take the average value, where the values are just 1, 2, 3 up to 13. You take the average of those 3, and you're saying what proportion of those averages are, for example, 6. And you say, well, about 15% have value 6. What have value 7? About 17 or 18% have value 7 as the average value among all these groups of 3 cards. The point is that, and we'll go on, 4-card hand is even more peaked, 5-card hand is even more peaked. The point is that no matter what you start with, as you take more samples of larger size and take their average value, you get a distribution that looks very much like a normal curve. And you can see here that we've superimposed this exact normal curve, which is the smooth curve, onto these dots, and you can see that the dots line up almost exactly onto that normal curve. So, in fact, it doesn't matter what distribution you start with. If you take collections of a certain size, like sample size 2, and you take their average, and then sample size 3, and you take their average, and sample size, in this case, 10, and you take their average, you get something that is closer and closer to a normal distribution. And in fact, you can say specifically how wide that normal distribution is. That is, what the standard deviation is of the approximating normal distribution. And it is if you have something of samples of size n, it turns out that the standard deviation of that approximating normal curve will be 1 over the square root of n times the standard deviation that you started with. In other words, you're getting more and more peaked as you take bigger samples. And this is going to be crucial when we discuss the issues of statistical inference. These are actually the workhorses for statistical inference. And by the way, the fact that you get a normal approximation and its standard deviation is decreasing by the square root of n as you take samples of size n is called the central limit theorem. It's central to statistical inference. Well, in this lecture, we have introduced the famous bell-shaped curve. And this normal or Gaussian distribution arises in a lot of settings, like heights of men, scores on tests, measurements. And when you have many small factors that are contributing an error, pushing it up or down, you can expect a normal distribution to arise. One of the main ways that we try to deal with distributions is to approximate a distribution by choosing one of a well-known family of distributions, such as the Gaussian or Poisson or binomial or uniform distributions. And then choosing the parameter values so that we have an approximation that does in fact fit the data. It's at the right place on the graph. It's centered at the right place. It has the right standard deviation. So if we have a physical reason for expecting a certain kind of distribution, then our challenge is to get a good summary is to find the values of the parameters. And that's one of the big goals of statistical inference. If we know the mean and the standard deviation of a normal distribution, then we know for sure that 68% of the data are going to be within one standard deviation, 95% are going to be within two standard deviations, and 99.7% of the data will be within 3 standard deviations of the mean. If you can talk about the number of standard deviations above or below the mean, allows you to compare elements from 2 different distributions, and that's called their z-score. That makes a meaningful comparison. In the next lecture, we're going to talk about correlation and regression. I look forward to seeing you then.